Hello, Professor Luis Carlos. I'm Victor Cornejo, and this is my evidence number 2, where me, along with my peer from Fervat University, developed a controller for a second-order system that we solved previously. Now, the methodology we followed for this system was to first identify the system as a second-order system. This condition was given to us because of the schedule we had, but we first us had to identify the system and use the corresponding equations to later solve the system. This was the next step. After we solved the system and obtained our transfer function, then we designed the controller around that transfer function we obtained. Now, next was first modeling the equations for the second order system. We input the system, we draw the circuit, I mean, in Fawcett circuit to obtain data and export that data to MATLAB and test how the system performs. After that, we need to obtain our transfer function, which is the transfer function g in the complex variable S domain, which means our transfer function would be VO, or voltage from the output, over the voltage from the input. We used Ohm's law and Kirchhoff's current law to solve the system, and we obtained our transfer function so we can work around that transfer function to design the controller. After that is the controller design. Because we had the second order system, we were told to design a PI controller and a PID controller. For each of those controllers, we used a different technique to find our proportional, our integral, and in the case of the PID, the derivative components for our controller. For the PID controller, we use the pole compensator method to find our 3 parameters we needed. And for the PI controller, we used the Ziegler-Nichols method to obtain our 2 components, the P and the I components. After we obtained those parameters for each of the controllers, we input those parameters into our block diagram, sorry, and we ran simulations to see what results we got. Now, another technique that we could have used, but was not taught to us during the course, was the control Lyapunov function. This function comes from the ordinary Lyapunov function to test if a dynamic system is Lyapunov stable, that's the name, or if it's asymptotically stable. To test if the system is asymptotically stable, which is the best case scenario, it has to meet some criteria. The state vectors x and u have to belong to the real numbers domain, and the system must begin and end in the same domain as the chosen variable. If all of these criteria is met, then we can use the control Lyapunov function to control our system. We have to develop the function so we can put it in our controller. Now, one of my classmates suggested the pole placement method, which is a great method, don't get me wrong, that can yield great results if done correctly. Any method can give you results if done correctly. But this method also uses heuristic results. There's nothing wrong with trial and error. I'm an advocate for trial and error. But in this specific case, I can see this technique used by more experienced control engineers, not so much for a beginner, especially in a simulation environment where we have the time and the resources to test if our system will work, but sometimes we don't have that freedom, and this technique can take more time. Now, as a closure, this course was very fun. I wish I had more time to let the topic sink in, but it was very fun. It was a different type of experience for me. Thank you, Professor. Hope to see you again soon.